All right, here we go. So we are going to actually pick up on page not 1, not 2, not 3, not 4, but 5. We're going to start on page 5, 3.2 exponential modeling. This is where we're going to start. All right. So constant rates of increase and decrease. Okay. So, but now if it's always increasing by 3 each time, that's a linear model. Okay. When that rate is constant in that fashion. When the rate is a constant percentage, it is an exponential. Okay. So suppose you rake the yard before you go and get the rake hung back up in the garage. There are 50 leaves on the ground. Okay? So in terms of a point that we could graph of our function, we would have 0 hours and we would have 50 leaves on the ground. Okay? After 1 hour, how many leaves would be on the ground? After 1 hour, how many leaves on the ground? 54? After 2 hours, how many leaves are on the ground? Can I have 0.32 of a leaf? Can I have, this is a legit question, because it depends on what we write down, right? Can I have 0.32 of a leaf? I've seen parts of a leaf before, right? No? Okay. So yes. Okay. If this were people. No. Okay. If this were hamburgers. Yeah. Okay. Right. So it all depends on what we're talking about, right? Okay. Right. So 58.32. After 3 hours. How many leaves on the ground? Sure. Right? Okay. How are we getting those, or how should you be getting those much quicker than how you are actually getting them? Grayson, how did you get yours? Multiplied every time by 1.08. Okay. And we could continue that pattern on. It's asking us for how many leaves are going to be in the yard 12 hours after we started. Okay. We could continue that pattern on. 12 isn't that far to get to, but there's got to be a quicker way. And that quicker way is we're going to make an equation of f of x equals a b to the x power, where f of x here is going to equal a, my initial value was 50, times B, which would be my growth rate, and my growth rate was 1.08 to the x power. So if I want to find the number of leaves on the ground after 12 hours, I'm going to find f of 12 by plugging in 12 for x. And I get that there are 125.909 leaves on the ground. Okay. Population P is changing at a constant rate each year, then P of T equals P sub 0 times 1 plus or minus R to the T power. Okay? You might have also seen it as P equals A times 1 plus or minus R to the T power. Now it says where T is in years, but truth be told, T can be whatever unit of time you're dealing with. Okay? So if we were doing, like we just used it in terms of hours. Okay? So we can use that same formula in terms of hours. It doesn't have to be years every single time. Okay? We could do minutes. We could do, days, weeks, etc. Just whatever unit it is in, that's what unit you then are in. Okay? So with that being said, then, determine the exponential function with an initial value of 12 and increasing at a rate of 3.5% per year. So we'll say f of x is equal to what? $12 times, no, 1.035 to the, in my case, it's going to be x because I went f of x. Okay. And then we can utilize that function going forward to find whatever it is that we need to find. Okay. So, you purchased a 1979 Ford Pinto back in 1985. So you purchased this rockin' car back in 1985 at a value of $1,800. Classic Pinto. Anybody know what the problem with the Pinto was? The major design flaw of the Pinto. Other than it being a Ford, yes. Okay? The gas tank was right behind the back bumper. So if you got rear-ended, the car exploded. Okay? That's why they don't make Pintos anymore. Okay? Alright? Okay? Alright? So white with red striping, Starsky and Hutch style, and sporty rims. It was all the talk at Greenway High School. Side note, this was Mrs. Hill's, for those of you that remember Mrs. Hill, Mrs. Hill's car in high school. Okay? Normally there's a picture of Kate Hill and Pinto in her driveway. Okay. Schmeling did. Yep. Mm-hmm. Okay. Hard to believe, but somehow this hot rod actually lost value at the rate of 7% each year. Find an exponential function that describes the value of this classic in terms of T years since 1985. Okay? So, we know that this hot rod was valued at $1,800 in 1985. Right? Is it increasing in value or decreasing in value? So what's my R then? Or what's my no? 0.93? Yep, 0.93. So 1 there wouldn't change it at all. Okay? If it's increasing, then we're going to add to 1. If it's decreasing, we're going to subtract it from 1. Okay? So there's that. Okay? So then what is the value in 1990? So what is my t value in 1990? It's 5, right? Okay. 85 was 0. 86 is 1. 87 is 2. 88 is 3. 89 is 4. 90 is 5. Okay. All right. So that means I'm going to try and calculate here, or not try. We're actually going to do. So f of 5 is going to be 1800 times 0.93 to the 5th power. What is the value of Trig Mama's hot rod back in 1990? How much you got? Okay. Good. Awesome. All right. So suppose the population of Austin, Texas is following an exponential growth pattern. In 2010, the population of Austin was approximately 1,377,000 people, and in 2020, the population grew to approximately 2.053 million people. Okay? We want to create 2 ordered pairs from that information. Okay? What's our first ordered pair? 0, comma, what? Okay, that's a pretty big number, right? So could we make that be a little smaller? We could do 1,377, and then our answer would be in thousands, right? Or we could do 1.377, and our answer, our data would be in millions, right? Okay, all right. So 1.377, and this is going to be population in millions. And this is going to be years since 2010. Okay? Both of those titles of those columns are very important. Okay? Year 0 is not 2026 years ago. Year 0 is 2010. So we need to tell people that. 1.377 is not 1.377 people. It's 1.377 million. Okay? So we need to do that. What's the second data point that we can come up with? 10 and 2.053. Okay? Now, we want to come up with an exponential model of the form P of t equals a times b to the t power. Okay? Well, I'm going to use both of my data points. One of the reasons why we made that first one be a 0 value since 2010 is because then I can do this. If I've got P of t equals a times b to the t power, then I can say 1.377 is equal to my a value times my b value to the 0 power. B to the 0 power is how much? It's 1. So this is really just 1.377 is equal to A. And now I found my A value. Okay. Now I can utilize that again, and I can say 2.053 is equal to, now I know my A value is 1.377 times my B, but my B is now to the 10th power. How would I solve that? Oops. Forgot that. And then what? Nope. The exponent would be to the 1/10th power or 10th root. Yep, both of those mean the exact same thing. I'll even write them both one on each side. Okay? So find me the 10th root of that. Yes? Okay? So my exponential function then is going to be 1.377 times 1.04075 to the t power. And what would the population be in 2035? What is my t value in 2035? 25? Yep. So we need to find p of 25. And I get 3.737416. But that's in millions. So really the population, and on the 25th year after this study, would be 3,737,416 Austonians. Okay. If I sketch this graph, it's going to be an exponential growth or an exponential decay. Growth. Big growth, like steep growth, sorry, this way, steep growth, or more of a slight growing. Steep? I go slight because remember we started at 1.3, right? And 25 years later, we're only at 3. So it's not really that big. I mean, it's big in terms of what it is, but our scaling makes up for that. So I would go with a slight growth. Okay, and then we can fill in some points here. This would be the year 0, 1.377. Then we'd have the year 10, 2.053. And then we have the year 25, 3.737. this would be that, and this would be population. Going the other way, when will the population surpass 3 million? Well, we already got 3 million, so let's go 5 million here. Let's change this 3 million. We'll go to a 5 million because then it's sometime past then, right? So we know right now that our number has to be bigger than what? It's got to be bigger than 25, okay? Because 5 million is more than 3.7 million, okay? So in terms of 5 million now, my P of t function was 1.377 times 1.04075 to the t power. P of t now is going to be 5, and I need to solve this for t. Using your vast mathematical knowledge, what should we do first? Divide by 1.377. Using your vast mathematical knowledge, what do we do next? Well, I solve an exponential. Okay, take the root of t. What? I can take the log of both sides, right? Okay. So t here is going to equal the log with a base of 1.04075 and an argument of 5 over 1.377. Now, if you've got a fancy calculator, meaning one of ours, an Inspire, or one of those like scientifical Casio type ones, okay? If you've got one of those, you can type this in as is. Okay? If you don't have one of those fancy ones, you need to use the change of base formula, which is going to take log of 5 divided by 1.377, and then you're going to divide that by the log of 1.04075. Either way, I get a t value here of 32.287 years. Which would be in March of the year 2042. Right around the Ides of March. Okay. Good to go? What I would like you to now figure out is when the population of Madison will reach 1 million people. Go. So my A value is going to be 404 because it happened when my year was, or when my X value is 0. So then we've got 487 equals 404 times b to the 10th power. So I'm going to have 487 divided by 404 is b to the 10th power. Then take the 10th root in either fashion. And that gives me 1.6. So P of t here is going to be that. Then I want to know where that's 1 million people. So that's going to be, in terms of 1,000, 1 million people is 1,000. 1 million is 1,000 thousands. So then I'm going to divide by 404. Then I'm going to take the log. Get 48.507 years. So I would say for that one, June of 2050. Agree? Yeah. Shifting gears now, because what's the problem with unbound exponential growth? Let's talk Madison. Okay? So, because it's never going to stop, right? So it could hypothetically, over time, get to it. So like in 100 years, we could be living in Madison up here in Wausau. Because that city would just have to keep growing because there's spatial restraints to housing that many people. Agreed? Okay. Okay. So that unchecked growth isn't necessarily the best way to model data in real life. Okay? So what we have in place of it is something called a logistical model. Okay? Now, a logistic starts out looking like a exponential function. So it starts out and it grows exponentially, but then there comes a tipping point where that growth slows and it flattens out and it ends up being like this. This is a logistical function. Okay? Up in the upper right-hand corner of this page, you should put a, actually, I like, you got a grid right down in there in the middle of the page. Okay? So you've got a grid right there. A logistical function has not one horizontal asymptote, but it has two horizontal asymptotes. Okay? It has two horizontal asymptotes. Okay? A lower and an upper. And the function lives in betwixt those two. Okay? This lower one is very much so typically y equals 0. Okay? And this upper one is y equals c, and we're about to figure out what c is. Okay? All right? So logistical functions look like this. And c, so they're fractions, and c here is the limit to growth. It means that we are putting a logistical function has a maximum value that you can get close to. Okay? But you can't ever pass that. Okay? That's that c value. That's that limit to growth. That's that upper horizontal asymptote. Okay? Okay? Now, logistical functions are opposite of exponential functions. Okay? So an exponential growth had a b value bigger than 1. Okay? A logistical growth has a b value between 0 and 1, which means a logistical decay would have a b value bigger than 1. Okay? If you're using your exponential function as a natural log e value, then your k value here would be less than 0, and your k value here would be greater than 0. Because with e functions, exponentials base e, positive k means it's growing, negative k means it's k. Okay? We've already graphed it. We're good to go there. So let's come up with a logistical function based off of this scenario. Okay? What can you tell me about an initial value of 12? What is that point on my function? Say it loud. 0, 12. Okay? We want to come up with f of x function equaling c over 1 plus a b to the x. Okay? Limit of growth is 60. What does that mean? That's what? That's c. Okay? So right off the start, my function here is going to be 60 over 1 plus something. Oops. Almost went b to the b power. Okay. Well, we know we go through the point 0, 12, so let's type in, or let's figure out if f of x is 12, c is now 60, 1 plus a b to the 0 power. What's b to the 0 power again? 1. So this is really just 12 equals 60 over 1 plus a. I need to solve that for a. How am I going to solve that for a? I going to solve that for 1 plus a? So multiply by 1 plus a on both sides. Then divide by 12. Then subtract 1. So a is 4. Okay? So we've used our initial value. We've used our limit to growth. Now we should probably use that it passes through the point 1 comma 24, right? So I'm going to go back to my function, and now I'm going to say that 24 is equal to 60 over 1 plus 4, because a is now 4, b to the first power. Well, that's just 24 equals 60 over 1 plus 4b. Do what and do what? 1 plus 4b. Then subtract 1. Then divide by 4. And there's our logistical function. Okay? What I'd like you to do now is I would like you to find me a logistical function under those conditions at the top of the next page. Gracias. I get an a value of 5 and a b value of the cube root of 1/5. Questions, comments, concerns, clarifications? Okay. Let's graph a logistical function. This one has, first off, we can start with our horizontal asymptotes. It's got 1 at 0, and it's got 1 at what? 8. Okay? So we've got y, oops, step the brakes. We've got a y equals 0, and we've got a y equals 8. Okay? What's an easy point that I can find that it goes through? 0 for what? The y-intercept, we call that? Yeah. Yep, okay, so I plug in 0. Okay, so if I find f of 0, that's going to be 8 over 1 plus 3 times 0.7 to the 0 power. 0.7 to the 0 power is 1 times 3 is 3. So this is really 8 over 1 plus 3. 1 plus 3 is 4. 8 divided by 4 is 2. So my y-intercept is 0, 2. Is this a logistical growth or a logistical decay? Growth or decay? It's a growth because b is less than 1, right? Yep. Okay. So it's we got to think opposite from exponentials. So this is a growth. So it's going to start out low, come through, level up. Okay. Good times. Good times.